Hello everyone, we are Team Antibot. This is Leila, this is Datuan, this is Richen, and me, Baiye. We are in the studio of SEAL. We are interested in the behavior of robots, so we are exploring the potential of how these robots could behave related to each other through the interaction between them. Consisting of mobile, aware, autonomous robots, they are capable of constant exchange of information, interaction in real time, based ecology through its sensory system to obtain adaptive configuration in time, context, sight, and active presence. So first, we start our initial research, which we can do with the whole different robotic system. So we introduce external stimulus or magnetic behavior and insert into our robotic units to become internal stimulus affecting the behavior of units. By adding different sensors, we can achieve self-assembling. Based on these factors, they can achieve self-assembly and they can achieve collective behavior. They could achieve. So we are proposing an adaptive ecology of stimulus-responsive environment, which is able to adjust duration of population as factors of assemblies and structuring, so the system is capable of constant exchange of information interaction in real time through its sensory system, responding to the change of environment and human behavior. So first is our initial study of interactive stuff. The first is research about small agents by using the magnet behavior to see how they can behave by rotation and the moving of the position. And the next one, the next one is the single units, which we can collectively move them together to form a linear or a closed structure. And then we start to design units which have the ability to be mobile, and it will respond to the stimulus. So you can see the unit here, which is mobile, and we have the light as a stimulus, which is respond as magnetic behavior. So next one is.
We started also with the prototype communication. So communication plays an important role in our system. We did some kind of, we used some sorts of sensors like color, distance sensor, and light resistor to enable our robots, our unit, of communication with each other. Later on, we defined some kind of modes to help them communicate among each other and with their environment. So this one shows a kind of the initial communication studies. They were interacting with each other. And not finding another unit, after a specific loop, they were changing their search direction, and finding an obstacle on their way, they were avoiding that.
So we internalized the magnetic behavior and repulsion into our agents so that they behave in autonomous but not random way. Through calculating forces based on polarity and distance, their interaction begins. By changing parameters like magnetic forces and unit direction, they behave differently. So overall, they're able to change direction, running towards or leaving from each other. This is a simple magnetic simulation. So, those patterns shows with 2 or more than 2 agents, they're having very complex behavior. Those are the patterns. If we distribute a large population of agents and they have awareness of other agents within a certain range, they're able to self-organize into a grid pattern through implementing distance adjustment and searching for neighbors in range. With that strategy, units are capable of self-organized generatively into different patterns.
Okay, next stage is our prototype research. And based on our previous unit prototype, which can be mobile in 2D, and we added 2 wings on both sides of it, aim to achieve aggregation. Like this diagram shows the evolutionary prototyping. And yeah, this one is based on our previous prototype, and we added 2 faces, which can be achieve the 3D aggregation. So at this stage, our unit can move from point A to point B in 2D, and then it can carry out the other robots, like video shows. And we also trying to put 2 passive units besides each wheel, so that the active one will be able to stand up, and it is totally different from the previous behavior method. And this diagram shows the next version of our prototype. Based on the previous study, we realized that the face with 2 hexagonal pieces is not stable, especially after 2 units aggregate together. So we put 2 triangular pieces on each side of our unit to make the faces be more stable and integral. And this is our prototype. So we also use the acrylic material to reduce the rotation friction. The faces of this version can rotate more smoothly. And we can also use this prototype to achieve the 3D aggregation, like the video shows. After this, we realized the face of our unit rotate as a whole shape is kind of a limitation for 3D aggregation. To be able to give our system more flexibility and more stability, we designed a face with 2 separate rotation surfaces, which enable our unit to be capable of packing with others in any orientation and the angle. And the 2 hexagonal surface angle is 45 degrees to be able to make the whole structure more stable. Yeah, this is our gearbox to trying to reduce the speed of our rotation phases, so that when they aggregate each other, the whole structure can be more stable. Okay, this is our prototype test for the separate rotation. And afterlight, which we achieve by using this unit to lifting the other robots up for 3D aggregation. Then we came up with we further optimize our robots by using 2 faces through 3D printing. Later on, we're trying to use our prototype, as you can see in the video, to make a self-structure. The middle one can send signal to the ends of robots, and then at the ends of the robots can push in to form like a structure, like arch. Yeah, this is a self-structuring in high population. And we are also trying to explore the enclosure architecture. So we came up with an idea with an airbag like the car. So we also use this 2D configuration to form like an enclosure structure. And in this diagram, we're trying to do some geometric study. And the basic rule for our aggregation is symmetrical and maximize our faces to be able to make our system more stable. And this is a basic 2D configuration exploration. This is a linear one, and this can be popping up sequentially to make a 2.5D structure. And this is another configuration. And after our experimentation, we found this basic configuration is ideal solution for our 3D aggregation to be able to make it more flexibility and diversity. This video shows how our system works.
Our units are mobile and self-aware on their own. However, they are more dynamic, complex, and powerful through interaction and communication with each other. So first of all, with any random distribution, our system is able to order themselves together. This video shows we distribute them randomly and then they come together. The video shows our prototype are doing exactly the same. Our unit first sending signal to others within a certain range, and then adjust distance in between to organize them together. Afterwards, they rotate themselves to fit in the pattern. In this particular scenario, our agents from a organized pattern is sending a signal of having a missing part. Then the other unit within the range receives the signal and comes to complete the pattern. We abstract their popping up process and discovered the choreography detailed. Their connections are rotating in a sequence that from the corner to the center. Through large population simulations, we have an intuitive understanding of how pattern behaves if joints rotates its sequence with different angle. Through changing parameters as the rotating angle of each joint and trigger position, they behave differently in speed, height, and shape. So, continuing with 2D organization study of our system, we also define the direction of each unit. Therefore, when they are joined in position, we are able to connect with each other through local rotation. And then they will pop up like a semi-doll. This is a catalog showing they never joined the similar grid. It's totally generative. From then on, we're considering the whole process from migration to self-structuring logic. With understanding of different environment, they may behave like insects and do different things according to criteria of context. In this case, our agents behave. This is a migrating process. They'll find the open space and trying to understand space by covering the whole area through interacting with each other. Then they will understand the density of the whole area. So in this case, some of our agents behave like leaders to send signal to other agents in different radius and adjust the distance in between. Therefore, a packing logic is generated. Afterwards, they will call for other units to help them to cover the space with minimum amount of units. We can use our, sorry. We can use our system freely since we are no longer organize our units into a unified grid. They can treat every group as a small system themselves and have different behaviors. In this whole organization is trying to cover the area with most amount of units, and every group is in their own particular order. So we made the simulation of a general collective behavior, then we are research in details of structural plausibility. So first of all, is there a detailed popping up sequence, as we said before, from the corner to the center. So this catalog shows there are parameters like quantity of units, rotation angle, and how many generations we pop that controls different configuration. So for instance, the low rotation angle will smooth the process, whereas the high rotation angle will increase the speed.
As our structure is a dynamic structure, we are having a kind of constant move based on conditions and data exchange. So our analysis are going to be on the real-time base, and this one shows that we are having a kind of carrying up and horizontal movement and some moments which are static, momentary. We did some simple simulations to know that how this popping up system and the choreography, it will affect our structure. So starting with the shearing forces, specifically because we have the connection between our units. So we were observing that we are having a constant change on the shearing force, which is the highest in some units. So moving from that, we try to employ some strategies to help our structure with that. At first, we were thinking that only on those units receiving the highest shearing point, we can increase the electricity to increase the magnetic connection on those. And on the second level, we can add a kind of sublayer as a support, which is something like a temporary scaffolding in constant move supporting that. But this one requires more unit numbers, and we are employing it probably at the times that we need a space subdivision in addition. And then for the addressing translational forces, we decided on a kind of base arch, means a kind of arch which is able to stand on its own foot without any support. But beyond that, based on the maximum reactional forces that we are having, we are thinking of having some support units in the horizontal or arch-based format.
So we're also considering of rotational forces. Our counter strategy is by increasing the width of the pattern. So in this simulation, the simulation shows the first structural strategies that has supportive sublayers. They are popping up with the main layer. So also we are having a substructure outside the main process will support the main from the foot to provide more frictions on the ground. By increasing the number in one direction, we also need to increase the quantity of units in the other direction against the rotational force. So this is the overall animation showing that when they are organized together as a pattern, and then they call for other units to support them. So the main structure starts to lifting up.
Energy sharing is also very important to our system because it can provide our system with some sorts of behavior. We are thinking of the wireless power transfer in our system. Units with a low energy level lower than the threshold, they will send a signal for this. And then based on the sequential a priority based on they will first ask the same arch, and then they will ask the units which are are not in the main aggregation, like the furniture or temporary scaffolding, to send them those kind of energy. And we are also thinking that our structure is going to be a kind of dynamic structure. This one shows a topological transformation, just one profile of our system, responding to the human and the human behaviors through the data scanning and tracking the people. So we could have different kind of configurations. And at the times that there is no human presence, our system can go to the equilibrium state, or it can entertain itself by opening up to the environment and inviting the potential users in. Oh, and last break. And also at times.
So we also design different configurations by using our system, because our system is a real-time based architecture adaptive space making machine, and they are capable of transforming from one configuration to another configuration. So this diagram is showing our system transform from one stage to another stage. So there are 4 stages here. You can see the basic configuration for our system. After this, we have a short video showing our one possibility of our system. So this is showing the basic configuration forming process. This one is a double arch, and then it comes to one big arch. And this is showing the cantilever. And this is showing the whole structure transforming. And this is a render showing the transforming from bird view. You can see it will change color according to the transformation. This is the down view, which is close to the ground. This is the render showing 3 stages of our system. First is the unit coming to the site, and then the unit come to interact with people, ground, and then start to form in the structure. And the final one is the structure made by them. But the structure is not a permanent structure. It's a real-time based transforming structure, so it can change to another one. Okay, thank you for the phase 1. Ray 2, Marta, and yeah, thank you.
Tutors, thank you.
Wait, changed.
Yeah, I kind of would like to kick off because you make some big structural moves, and perhaps it's appropriate to comment on that a little bit. I think you're overestimating a little bit what these little guys with torque can resist and what these servo motors can give you, because you're before you reach a stable section, you kind of are engaging all these motors to do their best and not to kind of burn up and try to collapse. So why I'm saying that is because I think you perhaps have missed a small opportunity, and that is that in your direction to start to generate larger space, you go to linear elements. And these linear elements can only be stable in that direction. So until they are a stable arch, you need to have all these motors act and keep the structure up. So I would have expected in these kind of assembly systems that you would, and you saw it also in your models, they look to me a bit like these bodybuilders or weightlifters that barely get the next one up. So to focus on that and to focus on that observation, that they're good at maybe positioning and bringing one or a few up, but then you get to a stable section, right? So you can look at that in an aggregation so that it's always a local one that does the lifting, and you reconfigure to then always stay in stable sections and to make this realistic. And that's the issue with the linear kind of relationships. Another possibility is not to go to aggregations that then balance and always pick up, and you could even imagine instead of keeping your connectivity, your topology continuous. You could also, one part could be moved to the next one and build up and so on and so on. And so there is no reason to keep these strings always continuous. But another aspect is certainly in this, if you're interested in these linear ones, one way to actually get to a shape that is not at all a structural shape in one direction is to actually go to, for example, arches in the other direction. So to actually use the 3D, the surface that you have, and not to split it up in single arches that need to do all the work, you could have done much more. So you could have done something that looks totally non-structural, but that impression is taken because you have structural arches in the other direction, for example. And so I just wanted to say that there I think you're being, well, not even a bit, but a little bit over the top optimistic. So that is.
In the configurations that we had started some studies also in another, but just to remind you that all these models are some sorts of models which are showing the behaviors that we are trying to achieve, and that is our trials for that.
Understood, but you did present almost half of your presentation was on the structural possibility, so fair enough that we comment on it.
Thank you.
Yes, I'd like to comment on that too, because I mean, I'm fascinated at one level, and it's in many ways there's a sort of poetry here of the structure, but it's a bit like being at a very early stage in the Middle Ages, where actually these are nothing more than a piece of cut stone from a Gothic vault or Romanesque vault, and we're going through that extraordinary process that the Gothic development from sort of massive masonry to lighter and lighter structures, and in that sense, it's these chunks of stone, it seems to me, are somehow have to be seen as a very early stage. And I'm trying to imagine where this might get to if you had another, 5 years to work on it. What would happen? And what would happen if you've got the same problem as the first project? It's all node. Part of the answer to your question must be to break away from the very expensive energy, time, effort, effective nodes, which you have to do to get this far. And I understand that because that's what this exercise is about. So congratulations on building the node. I'd like to hear more from you about where you think this would go to when we got past just a pile of chunks of stone on the table into something really that uses the intelligence that this potentially has.
Scanning and the human interaction, and the environmental thing. But I mean, yeah, something like that for the time being. But we are not thinking of something like exactly like a very intelligent IBM. I mean, in systems.
Actually, we are just using the simple behavior to achieve what can achieve in the system. So basically, the unit is quite simple, but they can have very complex behavior. Currently, we just explore like this, but I think in the future, they can achieve more.
I'm going to pick up a little bit on what Philippe said, because besides the structural comment, which I think it's obviously very clear, I think there is something here, and also picking up on John's building block idea, is that such a system would be, or I think one of the most potentially applications of such a system would be in a, for example, inaccessible site, where you have the units that are deployed and the units are able to find each other because there is no one to assemble them. Yeah, so that is the beginning principle, I think, of such construction system, is that nobody can be there to put the units together. They put together themselves, let's say. They self-assemble. So you could have, I think that you could think about this as a site where the units are actually deployed from different points, and therefore they have to look and seek for each other, or else it's a system that is deployed from one single point, and the units are able to move onto each other in order to position themselves where they have to end up in. And I think that this is really, at the end, what to me is a little bit unclear yet. How do you go about if one or the other? When a unit is able to move, to take one unit and move it over itself in order to position it somewhere else, the whole system could act as a distribution system of the units anywhere they want, yeah? So in a way you could say they can be deployed all from the same place because the system will work in such way that it can deploy material wherever it wants. So they don't need to find each other, let's say, because the system is able to do that. And then I think really these kind of robotic, lightweight building blocks become incredibly powerful because it's about deployment more than it is about structure per se, I would say.
Well, very impressive, obviously. The amount of work is staggering, and the various layers you address and work through and solve problems. You've reached very far. You're overreaching at the same time also, I mean, as Philip was saying. But I want to pick up two threads. One is the idea here of that smart brick being the only substance at play, but you already started. I think there was a criticism, and you picked up on that. You're talking about active and passive elements, and but we don't know. It was mentioned once how this later plays out in the structures, not yet. But I think that's an interesting passage, and also the the degree of some kind of energy economy you have addressed with the energy sharing and so on. So that's smart. But another point I think we need to start discussing is the behavioral and strand of research here. So to what extent is that really a bottom-up agent-based process where we would discuss rules, and to some extent that's the way you started here, obviously. I guess we need to see. But when we're talking about some of those global constructs, which are ambitious, where a lot of elements have to come into specific configurations. What are the feedback mechanisms? What are how is that structured? Is to what extent you need an external computational center, which organizes that. And the whole discourse of robotics and swarm robotics with leadership and following, active, passive, is a domain which is prevalent. I mean, I think the bottom-up agglomeration would not be able to be so well ordered and ambitious in the overall. I mean, it was unclear. Some of these patterns you're hinting at had this kind of each time different. You talked about a generative pattern, but then that was lifted into a dome, which most of it couldn't sustain. So I think there's a lot of open questions, and it's very stimulating raising these questions with this kind of fantastic dream project.
I think that you're raising a really good point where at a certain point in your presentation you talked about leadership, and I found that very curious. And I look at all of these configurations and I start to understand that there are in fact these dense moments where you have to launch the system somehow, right? And that kind of brings a larger point. I mean, Theo's description, which I love, is this sort of human-computer or human-machine symbiosis that has to somehow occur. I mean, in kind of Theo's call of our architecture will be autonomous, will sense, etc. That amazing list that's kind of launched your studio, I assume. And I wonder a little bit about that and whether it's been, in a way, interrogated enough. There were certain moments where we certainly saw that your units could sense maybe there's some proximity sensors and they would always stay 10 feet away from a human being, right, or something like this. And so there is a little bit of intelligence there, but I feel like I'm sort of missing a little bit of the human-computer interaction, and both it's at a generative point, who guides this thing, how does it anticipate programmatically what these things are up to, right? Because clearly you're thinking of this as a kind of an architecture that's for humans. And so we have different desires, our motivations are unique. And so there's got to be some much more active way that your ecology, let's say, is evolving in tandem with some kind of human desire. Because right now they're sort of, they're sort of motivated by structure, but for structure's purpose. It's not a kind of a symbiotic relationship yet. So for me, that's the kind of the big hole right now, let's say, and maybe one of the most complex holes. I mean, we have huge research clusters at major academic institutions studying that very issue, right? HCI is huge. Interaction design is huge. And so I think for me, that's where this gets very interesting and maybe less kind of linear and less obvious. Humans are not necessarily motivated and do not necessarily want fluid experiences, right? We might want glitchy experiences. We're attracted to things that are less fluid, at least in my opinion, right? We want corruption. We want, we enjoy failure. We enjoy things that have personalities that are abrasive, right? And so right now your units sort of follow the rules a little too much. They don't yet have a kind of quirkiness or a personality that one would expect in such a system. But that being said, I think it's an extraordinary body of research. Yeah.
Yeah, I mean, in terms of everything that's been said, I mean, I would support all of it. But I think Jason, your point about the human aspect is part of course, driving conversation. But it's, in one sense, I think where the strength of the project lies is to identify that on the individual unit, the communication between each other, the playfulness, the search mode, the idea of sorting from a random state, all of those time-based kind of scenarios are something which we also found a bit of our limits in, being really honest about where we were. Because I think the motivation was never to create structure, but was to create space. And the students, as they were trying to demonstrate the capacity to have basic sensing orientation and so forth, focused on that for almost all of the studio. So it's completely fair assessment from Philip that the structure is overreaching. And to be honest with you, they were working on trying to find ways to collectively self-structure these things. And I think at some moment it became more serial repetition in terms of what they could achieve with 15 or 30 units. How did then they cope with a population of 10,000 or 100,000? And as soon as scale was identified, where this wasn't just a piece of stone, but it became almost an urban toy, I think the illusion of the kids running around with it is a very important feature in this, because we need to identify what role would this actually have. It wouldn't be to facilitate a function of creating an office or a kind of responsive environment for the sake of it, but it was used as a kind of generator within particular passive public spaces as a way to animate and to bring people together. And particularly with a kind of square culture in the UK, it was thought about. That being said, I think the idea of the organization is something that they need to sort of work on, and the idea of generating goals, that things are not prescriptive. To address Patrick's point, I think they try to find a way where they are able to negotiate a sorting out organization which is random and time-based, converging, and then trying to elicit from the populations that they have what plausible scenarios could they create. And that's something that they keep repeat the idea that this is time-based and transformative, because a solution space is never the initial, And over time, this would have to find ways of conditioning itself and building fitness criteria that would have to be based on occupancy or integration between infrastructures. So it is a bit of a clumsy system that sorts and iterates and tries to create criteria. On the other hand, I think, with that being said, they were exploring the idea that things could be 2D organized. When they get this convergent, that 2D organization then gets the patterning of the geometry of these angles and the geometrical body plan of each of these individual elements. So in one way, I think they are a bit clever in trying to use the intelligence of geometry as a way to help the sorting, because I think it wasn't something that could be completely command control center distributed like that. Even airports are not really working on the populations that the project would demand. And so I think that there is an intuitive sensibility between pattern recognition and using this to inform space making and the idea of migration and kind of more agent kind of logics to identify at least a sense of space and the relationship to context. So for me, I think it's just at the beginning, for sure. And of course, it hasn't met the conversations that we've had. But I think it's really important in the studio that they find ways to demonstrate elements of it. And I think that's why there's been you'll see that there have been many iterations of these kind of individual units. They don't really look very different, but embedded within small decisions are radical behavioral differences. And that teasing out, I don't think we found the right way to communicate that yet. So, but I think in terms of it, of course, it leaves a lot to the imagination, but I hope that imagination is something that is given some legibility based on some of the demonstration that they have.
Also, the imagination was triggered by the amount of fun you had with this project. It was in between with a disco, there was like a disco, so that was very pleasing to see, and so thanks for that. I think also the decision for the scale of this was a crucial moment. Of course, we talked a lot about this now. If you would ask me, I see in these drawings much more like a snapshot animation, so it's much more showing a behavior less than a spatial structure. And I think, for example, this system embodies basically all the aspects, urban mobility aspects of it at the moment. So there's aggregation, flows coming together, going apart from each other. So for me, I look at this as a kind of the smallest mobility unit, vehicle. So this is the interpretation I would look into this, and maybe also open up the discussion and going away from the scale and say, like, you're looking at the system, organizing systems and flows, what could they be applied for differently? Do you sailboats, basically? We should talk about that later. Fantastic work, super interesting. That's back. So yeah, fantastic work, super interesting. Again, it's a kind of monomaterial, one cell does everything project, apart from at the moment, which Patrick picked up on, where you talk about this the dead cell. And I think I would like to see an extension to the project, which is a kind of temporal dialogue, that of course you're redistributing matter, and you can do it now in a way that's far different to typical, which gives cities completely different fundamental opportunities. But I'd like you to maybe look at how you could structure your systems of thinking around that. So this is great for the city. You could do temporal devices, and the sorts of imagery you're talking about looks temporal, and it's great. If you had 100% moving cells, then it's great for temporal. But the city also has, I think, an idea of, or you could bring to this project an idea of calcification, where by changing the percentage of dumb cells, that these things could reconfigure, serve temporal needs. If those needs turn out to be actually more persistent, then they could slowly start being like, okay, we don't need all the smart guys here. I'm going to replace myself with a dumb guy and head off and do something else. And in so doing, I think you could really enrich the potential of the project. I also really like the idea, like, because these guys have, of course, remind me of ants making ant bridges that are 100% ants. But I also really like the image of the ant who's carrying a piece of stuff that's bigger than himself, so heroically, along to deposit selflessly somewhere else. And this kind of bricolage thing that you'd have a structure that had some percentage of really smart guys, and then whole big chunks of car doors or whatever's been the detritus of the city having some second life, this kind of Lebbeus wood scabbing, or some kind of dialogue to the project which says maybe it's fantastic to distribute in an incredibly excessive way this much intelligence, but at times you could have less. You could have more dumbness mixed with the intelligence.
I think another thing that you're doing that's probably novel, that I've seen very rarely in swarm-based projects, is this sort of sharing of kind of energy across the system, sort of this middle kind of investigation. I think there's something for me particularly latent about that territory, and whether you realize it or not, I think you're contributing something novel there, that in some ways you're cross-connecting energy cycles, and that maybe makes me think a little bit about the limitations of these three boards, where you're really just kind of interrogating what it's going to be like at night, at this kind of penultimate moment when there's kind of rain on the ground and everything looks sexy. The reality with a system like this might be that it might only need to do that for 6 hours of the day. And so what in fact is it doing with the other 18 hours of the day? Well, in fact, it's a rather energy-intensive system. And so it's going to be, in a way, seeking out energy. Is it generating its own energy? Is it a parasite? Is it stealing energy? Is it reconfiguring to optimize itself relative to the path of the sun? In fact, maybe that's another avenue. So its motivations, I think, are both towards humans, but also towards the colony, let's say. And I think there'd be a very interesting set of diagrams that might be talking about that, because for me, that's when then a lot of these configurations might make sense. There's an internal drive. It wants to live, right? And if it doesn't gain enough energy, it won't be able to serve us and also the colony, right? So there'd be, for me, something very intriguing about that kind of double-sidedness of these units, and I think it would really push the project into a very interesting domain, I think.
Okay, I think we'll leave it there. We'll break for 45 minutes and kick off again with the next three projects.